Bismillahirrahmanirrahim. This video is primarily theoretical type. We'll discuss the transformer phasor diagram, how to draw it, and at the end we'll also find the approximate equation for transformer primary voltage with the help of a phasor diagram. Now we'll start with the what is known as transformer voltage regulation, and this is one of the formulas given, which is Vs no load minus Vs full load, S for secondary, divided by Vs full load. Let's see from this diagram here is the primary side and secondary side, and when nothing is connected, then it will become V secondary no load. And when we connect a load of full capacity, then we call the secondary voltage as V secondary full load. So this is what has been used here. Vs no load minus Vs full load divided by Vs full load for the voltage regulation. Now, what is the importance of voltage regulation? Let's say we want to purchase a transformer and we want to compare the performance of two transformers. So the one with the lowest voltage regulation will be better. So from here you can see that actually what is voltage regulation telling us is that if you connect a load, then the voltage without load should not drop much. That is the main thing. So if the voltage regulation is low, that means it is a good transformer. There is another way of writing the Vs no load. That is from here you can see that Vp and Vs are related by A. So from here we can find Vs to be Vp over A. So we replace Vs no load as Vp over A. Now, how to determine the voltage regulation? There are a couple of things that we have to keep in mind to determine the voltage regulation of the transformer. It is necessary to understand the voltage drop within it. So what is dropping this voltage is these parameters. Inside the transformer, they cause the voltage drop because of the losses inside. And this is called the excitation branch. So it's saying that effect of excitation branch on the transformer regulation can be ignored. So only the series impedance need to be considered. So this is series impedance and this is the excitation branch. So comparatively, loss in the excitation branch is less. Therefore, for approximation, we can ignore this. And so our circuit will look like this. The easiest way to determine the effect of the impedance and the current phase angles of the transformer voltage regulation is to examine the phasor diagram. So by looking at the phasor diagram, we can see how much is dropped at which point, especially in the resistive part, in the inductive part. So we start with writing the KVL equation. So we write KVL equation from here, minus VPA R equivalent IS, X equivalent IS, and the terminal voltage Vs. From here we get this equation. So to find VPA, we have to plot Vs, we have to plot R equivalent IS, and we have to plot X equivalent IS. Let's start. We assume that the Vs is in phase. Following phasor diagram, the phasor voltage Vs, that is the secondary voltage, is assumed to be at zero angle. And all other voltage and currents are compared with this reference voltage. So this is Vs, zero angle. With that, we have shown the current flowing, which is at some angle lagging, theta angle lagging. So the first thing we'll plot is R equivalent IS. We know that the current voltage drop in the resistor is in phase with the current. So this is R equivalent IS. And now, because of this J, the inductive component will be leading by 90 degree. So the inductive component is leading by 90 degree from here. So what all we have got now is Vs, we have got REIS, and we have got JEQIS. So now we can connect the tail and head to find the final Vp over A. So this connected gives us the Vp over A. So from here, you can now easily see how much is the drop in the resistor, how much is the drop in the inductive component in this, and what is the primary voltage, what is the secondary voltage, etc. So a transformer phasor diagram is just a visual representation of this equation. So coming on to this, we'll consider now three cases. If you look here, this is already we have discussed the power factor is lagging. That means the current is lagging. So in this case, graphically you can see that VPA is greater than VS. And therefore, from here, we can say that if this is greater than this one, then VR or the voltage regulation will be positive, greater than 0. The second case, we assume that the current is in phase with the voltage. So the current is in phase with the voltage. And in this case, also, now you can compare VPA and VS. In this case, it was much difference, much more than in this case. The difference here is less, but the formula remains same. That is, VPA is still greater than VS, and that means VR is greater than 0. The third case could be, okay, however, this time the voltage regulation is comparatively smaller because of the difference between the two is less than what it was here. And the third case is when the current leads. So this is in case of a capacitive load actually. The current is leading, and so we plot R equivalent parallel to this, R equivalent I. 90 degree, we get J equivalent IS, and connecting this, we get VP over A. Now here you can see that VP over A is less than VS. What will happen to the VR? The secondary current is leading, the secondary voltage can actually be higher than the referred primary voltage. So if the secondary voltage is higher than the primary voltage, that this happens, the transformer is actually having a negative voltage regulation because this is greater than this one. And negative voltage regulation means the voltage increases with the load. So as we keep on increasing the load, the secondary voltage increases with the load, and this is reduces. So this is undesirable condition. So these are the three cases that we discussed. Now we'll go for the determination of approximate equation. This was the proper equation, but can we reduce it? Can we further approximate? For that, we'll take help of the phasor diagram. You can see from here the difference between the two, but if we can bring it closer, like shown here, if we extend this line up to this point, Then, so if we extend this line up to this point, then you can see this is approximately equal to VP over A. Now, what is this line? We know up to this point it is Vs. So let's see what is the additional part representing. I've just colored it in two different colors, so we'll find them separately. Now the green part, I'm just cutting it and then flipping it in a manner that we are used to, that this is theta. So the green base will be R equivalent is and cosine of theta. So this is base of this triangle. This is hypotenuse. So base is the cosine of theta. Hypotenuse cosine of theta. So we can write this as R equivalent is cosine of theta. What about this other part? Okay, the first thing we did was we put a theta here. And why did we put a theta? Because you can see that the opposite angles, these two angles are opposite angles. This is 90, so this is also 90. That means this angle will be equal to theta. Once we have put in the theta, we are still going to find this length. So I have cut this portion as it is, and then I'll try to flip it in a manner which we are more familiar. So I have flipped it in a manner which looks familiar. So this is angle theta, and this is the hypotenuse part, and this is the perpendicular part. So what we are interested is in the perpendicular part, because this is equal to the purple line. So the perpendicular part is x equivalent is sine of theta. That means this part will be x equivalent is sine of theta. So now the approximate diagram, instead of this diagram, will be Vs Res is cos theta, and this Jex is sine theta. So our equivalent equation, or this simplified equation, will be as shown here. So this you can use if needed. I hope this gives you an idea as to how to what the phasor represents and how to find an approximate equation for the primary voltage. Thank you.